Welcome, I'm Nathan Weezy. I'm a professor at Marquette University. In this section, we're going to talk about the integral controller. Okay, so the first thing that I've done is in equation 1, I've written down the integral controller for a trapezoidal integration. So this is trapezoidal. And what we're going to do is we're going to do a sampling time of half a second when we do this, okay? Here, let's assume we have some plant that looks like this and we would like to control it. We'd like to pick a gain for Ki that will control this system using a sample time of 0.5 or half a second. So what we're going to do is do a method called the root locus, which essentially is going to tell us where the poles of the system land for various values of Ki, because it's the only thing that we really have to design here. It's the only value we have to find. We'd like to find one that's stable and that also gives us a nice, good response. Okay, so what we're going to do next here is calculate the open loop response. So remember that GOL in this case is simply going to be GC times GP. So we're just going to multiply those together. And equation 3 is essentially equation 1 times equation 2. That'll give us our open loop response. The last thing we'll do is find our closed loop response. So let's recall what that is. That in this case is just going to be GOL over 1 plus GOL. So equation 3 over 1 plus the equation 3 will give us equation 4. Now, what we will do with this guy, the closed loop response, is if you look in the bottom, it's not a perfect polynomial yet, but what we want to do is get it rational and nice and clean so that we can find the roots down here. And the one thing that you'll notice is Ki does show up down there. So essentially what I'm saying is the roots are going to move as a function of Ki. And what the root locus plot will do is show us where the roots are as we sweep various values of Ki. Okay, awesome. That's a very useful thing because then we can essentially check the whole infinite span of values for Ki and figure out what's the best Ki we can use to control this system. So here in this root locus plot, what we have here, you see these two x's? These are the roots, the starting roots of the closed loop system if Ki were 0. So essentially what this actually tells me is that the system's probably stable on its own without doing anything, which is interesting. But so if we use a Ki of 0, that's what we get. Okay, cool. So what'll happen now is as we increase Ki, the roots are going to move on us. So for instance, this root will move this way, this way, this way, this way, and keep going like this, all the way to over here. And vice versa, the other root will start over here at 1 and move inwards, and then they'll meet, and then it'll go this way, as you're increasing Ki. So this is very useful because now it gives us a kind of an idea of where we should put Ki. So what I'm thinking is if we want to have a nice good response that's cleanly damped and we want a natural response, it's nice and smooth and exponentially decays, we want to be somewhere along this line, right? That's where the damping ratio is 1. So once we stray away from that, once we go this way or this way, we're going to get some ringing in it. So I'd like to pick some value that would be on this line here. Any of those values are good. Now, it's not that these values here are bad, but as you go away from there, essentially you're going to have more ringing. Okay, so let's calculate some values and see what happens here. So one thing you can get out of this root locus plot is that essentially the whole system is stable for any value of Ki. I mean, over here it's going to ring a lot, but it's still marginally stable. So that's fine. So let's start small for Ki and just look at what happens when Ki is 0.06. So we calculate our controller in the z domain by just plugging in Ki, 0.06, and t is going to be half a second. We're going to go ahead and calculate the closed loop response then by plugging in that Ki. This would be equation 8. And essentially what we're going to do now is just look at the roots. So what are the characteristic roots of this? They're going to be this R1 and this R2. Okay, awesome. Where do they land up when we look at them? 0.77 plus 0.081, so they're going to be here and here. Okay, that's not bad with a K of 0.06. I mean, the damping ratio looks to be around 0.9. So you're going to have a little bit of ringing, but you probably won't even see it. So let's just take a look at the step response here. Oh yeah, look at that. It's not too bad. There's a step response. Kind of goes up there. So, getting away from the damping ratio of 1 by a little bit, it's not going to be bad. You're going to have a pretty decent response. Of course, you can see our step time here is half a second, right? So you got 4 steps in 2 seconds. Okay, and then the line down the middle here is just the step response of the continuous time system. So just as a reference to see how well this actually tracks a continuous time controller. Next, let's increase K a little bit. Let's go to 0.5. So now those poles are going to move again on us. Okay, so where do those show up? If we calculate our controller, we can easily do that, plug it into GCL. That's what we'll get for the closed loop response. So we'll have 10 is the controller and 11 is a closed loop response. If we plug that in and we calculate the roots of the denominator of the closed loop, these are where we can get 0.6 plus or minus 0.53. 0.6, 0.6. So we're going to be, call it somewhere here, somewhere here. Yeah, that might ring a little bit, right? We're looking at a damping ratio around 0.3 or 4, depending on where it is. Okay, let's see what that response looks like. And this is on the pole map by itself, but just to show you where it was with the whole root locus. Oh yeah, there you can see the ringing, overshoot, undershoot, and it settles down. Okay, that's interesting. Let me go back and throw on the root locus, these original ones, which were at 0.77, 0.77. So they were somewhere like right here, just to see track where we're going. Okay, so now let's do it again. Let's increase Ki and see what happens. Now we're going to check something a little bit more extreme. Ki is equal to 5. Wow, that puts them way over here now. Holy buckets. It's about minus 0.2 on the real side. So let's go look at this at our other plot here. Minus 0.2. So yeah, we're way up here now. Somewhere like right here. That's going to be bad. Damping ratio of less than 0.1. Wow. Let's see what that looks like. Yeah, look at this ringing response. I mean, it doesn't even really track very well the continuous time response. And the thing to note here is that we're ringing quite a bit. A lot of ringing in this response. Okay, one last time. Let's go up even higher. Ki is equal to 50, and let's see what happens. There are the poles. Let's look at that. That's interesting. Somewhere about minus let's call it 0.85. So I'm going to go put this on our plot up here. So minus 0.8, somewhere in here. I mean, this is way up there. You can see the damping ratio is almost towards 0, as if when we're residents, we don't have any damping. And let's take a look what happens. Wow, look at that response. That is oscillating a lot if you look at that. And it's hard to even see in here how much ringing is really going on, but it's a lot of ringing. So that's quite interesting there. And so this is a really bad response. But there's a good reason for doing this. It's so that we can understand where do we actually want to put the poles of our system when we're looking at the pole zero map in the Z domain. Okay, so we kind of already getting an idea where we want to put these in order to have a good response. I mean, we'd like to be somewhere over here. Okay, and these are good damping ratios, and we have good response too. So the other thing that's interesting to see is what about these natural frequencies? Well, what happens is if you go way up here like to 0.8 pi by t, that's good in terms of speed. Like that's going to make a really fast response relative to your sample time. But it gets a lot harder if you have any parameter variation. So like for instance, let's track this down. If we put a pole right here, right? And all of a sudden we have a little bit of parameter variation in our plant or even our sensing system, and we shift over here. All of a sudden we have really good damping at 1, and now we're at like 0.6, right? So there are trade-offs. It depends on, how fast you want to be and, how susceptible you want to variations in your plant, etc. But it's very useful to use this pole zero map to figure out where you want to push the poles of your closed loop system in order to obtain the response that you would prefer for your application. Okay, that concludes the talk on integral controller for digital control power electronics. Thank you.